Hello everybody, myself Prasant Mukhopadhyay, faculty member, Electrical Engineering Department, Pedagogical College of Engineering and Management. Today we'll discuss about some special type of thyristor, gate turn-up thyristors. In this lecture we'll learn its construction, circuit symbol, its volt ampere characteristics, principle of operation, and of course some commonly known applications of GTO. That means this lecture will contain introduction, basics of gate turn-up thyristors, its construction, principle of operation, J characteristics, and its applications. Thyristor, although is extensively used in high power applications, it always suffered from being a semi-controlled device. Even though it could be switched on by applying a gate signal, it has to be turned off by interrupting the main current using commutation circuit. In case DC to DC or DC to AC conversion circuits, this becomes a serious deficiency with thyristor due to the absence of natural current zero, as in case of AC circuits. So hence development of gate turn-up thyristor or GTO addresses the major problems of the thyristor by ensuring the turn-up mechanism to the gate terminal. So these are some basic real-life GTO which are found in the market. You see, so anode, cathode, and two gates are also being shown here. So how the basics of the gate turn-up thyristor? So gate turn-up thyristor is a three-terminal bipolar current control minority carrier semiconductor switching device. Similar to conventional thyristor, the terminals are anode, cathode, and gate. As name indicates, it has gate turn-up capability. These are capable not only to turn on the main current with a gate drive circuit, but also turn it off. So a small positive gate current triggers the GTO into conduction mode, and also by a negative pulse on the gate, it is capable of being turned off. That's why it is called gate turn-off. So in the figure, it is shown here that the gate has double arrows on it, which distinguishes the GTO from normal thyristors, because it is getting turned on and turned off are both possible here. So that's why there is a common symbol like this or this. So that means it indicates bidirectional current flow to the gate terminals. For on, it is one direction; for off, it is another direction. So the gate current required to turn up the GTO is relatively high. For example, GTO rated with 4000 volt or 4 kV and 3 kiloampere may need 750 ampere gate current to switch it off. So the typical turn-up gain of GTO is low and is in the range of 4 to 5. So due to this large negative current, GTOs are used in low power applications. On the other hand, during the conduction gate state, GTO behaves just like a thyristor with a small unstable voltage drop. GTO has faster switching speed than the thyristor and has higher voltage and current ratings than the power transistor. So several varieties of GTOs are available in the market with asymmetric and symmetric voltage capabilities. So GTOs with identical forward and reverse blocking capabilities are called symmetric GTOs or SGTOs. These are used in current source inverters, but these are somewhat slower. Mostly asymmetric GTOs are used due to their lower unstable voltage drop and stable temperature characteristics. So These asymmetrical GTOs have an appreciable reverse voltage capability, typically 20 to 25 volt, and these are used either the reverse voltage across it would never occur, or a reverse conducting diode is connected across the circuit. So we only our lecture will be limited only about asymmetric GTOs. Now its construction. So almost similar to Thyristor in its construction. It also has 4 layer, 3 junction like Thyristor. In this, N plus layer at the cathode end is highly doped to obtain high emitter efficiency, and this results in breakdown voltage of the junction 3 is low, which is typically in the range of 20 to 40 volt. Doping level of p-type gate is highly graded because doping level should be low to maintain high emitter efficiency, whereas for having a good turn-up properties, doping of this region should be high. In addition, gate and cathode should be highly interdigitated with various geometric forms to optimize the current to turn off capabilities, current turn off capabilities. This is a basic structure, there is cathode, these are the gate, and this is anode. So this is junction 1, this is junction 2, this is junction 3. So from this N positive, this cathode terminal is being taken out. From this P plus positive, this is gate terminal is taken out, and from P plus this layer, so anode is taken out. So the junction between the P positive anode and N base is called anode junction. N base and P positive. Heavily doped P positive anode region is required to obtain the higher efficiency anode junction. So the good turn-on properties is achieved, or the turn-up properties are affected, which says GTOs. And this problem can be solved by introducing heavily doped N plus layers at regular intervals in the P plus anode layer, as shown here. Okay. So the N plus layer makes a direct contact with the N layer at junction J1. We have seen in the figure. This causes the electron to travel from base N region directly to anode metal contact without causing hole injection from P positive anode. This is called an anode sorted GTO structure. So due to this anode sorts, the reverse blocking capability of GTO is reduced to the reverse breakdown voltage of junction J3, and then speeds up the turn-up mechanism. This is shown here. So, however, with a large number of anode sorts, the efficiency of the anode junction reduces, and hence the turn-on performance of the GTO degrades. Therefore, careful considerations have to be taken about the density of these anode sorts for a good turn-on and off performance. Now, how it operates, its principle of operations. For turn-on operation of GTO is similar to conventional thyristors. The anode terminal is made positive with respect to cathode by applying a positive gate current. The whole current injection from gate forward bias to cathode PPS junction. This results in the emission of the electrons from the cathode towards the anode terminal. This induces the hole injection from the anode terminal into the base region. So this injection of holes and electrons continues till the GTO comes into the conduction state. In case of thyristors, the conduction starts initially by turning on the area of the cathode adjacent to the gate terminal, and that's why plasma spreading the remaining area comes into the conduction. So unlike thyristor, GTO consists of narrow cathode elements which are heavily interdigitated with the gate terminal. Thereby initial turn-on area is very large and plasma spreading is small. Hence GTO comes into conduction state very quickly. So this is shown, explains here in this figure. So this is turn-on mechanism, and this is turn-off mechanism. The turn-off of a conducting GTO reverse bias is applied at the gate by making the gate negative with respect to cathode. A part of holes from P-base layer is extracted to the gate, which surfaces the injection of electrons from the cathode. So in response to this, more hole current is extracted to the gate, resulting in more separation of electrons from the cathode. It's shown here. Eventually, the voltage drop across the P-base junction causes to reverse bias the gate cathode junction, and hence the GTO is turned off. So during hole extraction process, the P-base region is gradually depleted, so that the conduction area is squeezed. As this process continues, the anode current flows through remote areas, forming high current density filaments. This causes local hotspots which can damage the device unless these filaments are extinguished quickly. So by the application of high negative gate voltage, these filaments are extinguished rapidly. And due to the N-base region stored charge, the anode to gate current continues to flow even though the cathode current is ceased. This is called tail current, which decays exponentially as the excess charge carriers are reduced by the recombination process. Once the tail current is reduced to leakage current level, the device retains its fault blocking characteristics. Now, this will explain the VI characteristics. During the turn-on, GTO is similar to thyristor in its operation, as I told you. So the first quadrant characteristics are similar to the thyristor. When the anode is made positive with respect to cathode, the device operates in forward blocking mode. By the application of a positive gate signal triggers in the GTO into a conduction state. The latching current and forward leakage currents are considerably higher in GTO compared to thyristor, and that is shown here in this figure. Is shown. So now the latching current and forward leakage currents are, I told you, it is higher than GTO. Gate drive can be removed if the anode current is above the holding current level, but it is recommended not to remove the positive gate drive during conduction and to hold at a value more than the maximum critical gate current. So this is because the cathode is subdivided into small finger elements as discussed to assist the turn-off process. This causes the anode current dips into the holding current level transiently, which forces a high anode current at a high rate back into the GTO. So this can be potentially destructive. So there were some manufacturers recommended the continuous gate signal during the conduction state. So this is the characteristics for blocking voltage. This is dot blocking state. This is gate triggering, the turn-on, gate triggered on. So this is on state and this is off state. So GTO can be turned off by the application of the reverse gate current, which can be either step or ram drive. The GTO can be turned off without reversing anode voltage. So this dashed line actually in this figure trajectory during the turn off for an inductive load. It should not be. It should be noted that during the turn off, GTO can block a rated forward voltage only. So to avoid DVDT triggering and protecting the device during the turn off, either the recommended value of resistance must be connected between the gate and cathode, or a small reverse bias voltage, typically of -2 volt range, must be maintained on the gate terminal. This prevents the gate cathode junctions to become forward biased, and hence GTO sustains during the turn off state. So in this reverse biased condition of GTO, the blocking capability depends. The blocking capability of GTO in reverse bias condition, so actually depends on the type of GTO. So asymmetric GTO has a high reverse blocking capability, while asymmetric GTO has a small reverse blocking capability. So that's also shown in the VI characteristics here. Okay, so so it is observed actually during the reverse bias conditions after a small reverse voltage 20 to 30 volt around. So GTO starts conducting in reverse direction due to anode short structure. So this mode of operation does not destroy the device provided that the gate is negatively biased, and the time of this operation of course should be small. So that in a nutshell about the VI characteristics of GTO, that is in the conduction state and in the off state. These are nicely depicted in this figure in different states. This for blocking state. So this is get triggered, it is turned on, then it will go to the on state, and when get triggered, turn off conditions, but turn off get triggered. So this will be the current direction, and the reverse blocking state. This is reverse blocking state. Okay, so that's all about the characteristics of GTO. Now, what is the applications of this GTO? So, due to the advantages like excellent switching characteristics, no need of commutation circuit, since it is a gate turn-off circuit here. Get turn off on thyristors, maintenance-free operation, etc. Next, GTO uses predominant over thyristor in many applications. So it is used as a main control device in choppers and inverters. And so some of its applications are area AC drives, DC drives or DC choppers, AC stabilizing power supplies, DC circuit breakers, induction heating, and other low applications. So that's all about GTO. So now we'll talk about IGBT, its principle of operation, characteristics, and applications. Now IGBT is insulated gate bipolar thyristors. So this is the symbol. Insulated gate, this is collector, this is gate, and this is emitter. This is the construction like this. So construction and this its working characteristics. This is the most popular and commonly used power electronic switch devices. This bipolar junction transistors and MOSFET. So we have already studied the BJT and the MOSFET working in our earlier semesters. So and how they are used in circuits, that's what we have studied. Now we'll discuss about IGBT, insulated gate bipolar transistor, its principle of operation, characteristics, and application. First of all, we show you a brief overview of this IGBT. This is the symbol, collector, this is gate, and this is emitter. This is the say practically available IGBT, how it is looked at. Now this is the say construction, and this is basically the working. This is voltage and collector current, and controlling voltage, different gate emitter voltage. So this is cutoff region, This is active region, this is saturation region. So later on we are coming to these questions. This is a most popular and commonly used power electronics switch devices. You know, basically you have already studied about that. This is bipolar junction transistors and MOSFET, metal oxide separated field transistors. So, we have already discussed about this in our earlier semester about this BJT and MOSFET, its working and how they are used in circuits, etc. So these are you are already familiar with, but these components have some limitations to be used in very high current applications, and some limitations to be used in very high current applications. So we move to another popular power electronic switching device called IGBT. So since we are talking about power electronics and drives, and since power electronics deals with a large power to handle with, so that's why this BJT and MOSFET, which we have studied earlier in earlier semester, so that will not of any use for high current application. So we'll learn about IGBT. So IGBT, you can think IGBT is a fusion between BJT and MOSFET. These components have input characteristics of BJT and output characteristics of MOSFET. So very interesting. So since it's the fusion between BJT and MOSFET, so its input characteristics is like BJT and the output characteristics is like MOSFET. So today we'll discuss about the basics of IGBT, how they work, how to use them in circuit designs, etc. So now come to the point of what is an IGBT. So it's the short form of insulated gate bipolar transistors. So it's a three-terminal device, three-terminal switching device that can be used for fast switching with high efficiency in many types of electronic devices. So mostly these devices are used in amplifiers for switching and trigger and processing complex wave patterns with pulse width modulations, etc. So typical symbol of IGBT, along which it's one of its images is shown here. This is the symbol of IGBT, and it's a typical use available IGBT. IGBT, as I told you, it's a fusion between BJT and MOSFET. Symbol of IGBT is also represents the same. So even see the input side represents the MOSFET with gate, and output side represents BJT with collector and emitter. So collector and emitter are the conduction terminals, and gate is the control terminal, which is the switching person is being controlled. So very interesting thing is that since it is a fusion of BJT and MOSFET, so MOSFET contributes its gate terminal portions, which is used for controlling purpose, and this BJT is contributing the collector and emitter portion for conduction terminals. So what is the internal structure of IGBT? So it is can be constructed with equivalent circuit. It consists of two transistors and MOSFET. As the IGBT possesses the output of the combination of PNP transistor and NP transistors, NPN transistors, and this MOSFET. So IGBT combines low saturation voltage of a transistors with high input impedance and switching speed of a MOSFET. Once again, I'm telling it combines the low saturation voltage of transistors with high input impedance and switching speed of MOSFET. The outcome often from this combination delivers the output switching and conduction characteristics of the bipolar transistors, but the voltage is controlled like a MOSFET. So once again, since it is a combination of two, this combination delivers in such a way the output switching and conduction characteristics of a bipolar transistor, and voltage control is like a MOSFET. So this is C, this is collector, this is emitter, and this is the gate of IGBT. So since it is a combination of MOSFET and BJT, they are also called different types of names. Different names of IGBT are, say, insulated gate transistors or IGT, metal oxide insulated gate transistors or MOS IGT, gain modulated field effect, say, transistors or GEMPET, and conductively modulated field effect transistors, COMPET. So these are the different names of IGBT available in the market. This, once again, I am telling you, this is insulated gate transistors or IGT, metal oxide insulated gate transistor, MOS IGT, gain modulated field effect transistors or GEMPET, or conductively modulated field effect transistors or COMPET. So how it works? So this working of IGBT is shown here. So IGBT has three terminals attached to three different metal layers. So this is these three terminals. See, these are attached to three different metal say layer. The metal layers of the gate terminal is insulated from the semiconductors by a layer of silicon dioxide. See, that is shown here. Silicon dioxide. This is silicon dioxide that is isolated from these terminals. So IGBT is constructed with 4 layers of semiconductor sandwiched together. The layer closer to collector is the P plus substrate layer. Above that is N minus layer. So this is P plus substrate, and that is N minus in negative layer actually. So another P layer is kept closer to the emitter inside the, and inside the P layer we have the N positive layers. See, there it is. See, these are okay. So the junction between P positive layer and the N negative layer is called the junction J2. This is junction J2. P positive and N negative layer means this is junction J2. And the junction between N negative layer and P layer is called junction J1. This is junction J1. Okay. So the structure of IGBT is shown here. This is like this. What I told you. This is depicted here. Now, to understand the working of IGBT, consider a voltage source VG is connected between connected positively to the gate terminal with respect to the emitters. See, positive with the gate terminal with respect to the emitter. Emitter is negatively connected with the negative terminal. Now, so now consider other voltage source. This is a VCC connected across the emitter and the collector. This is VCC is connected to the emitter and the collector. Collector is connected with the positive terminals, and with respect to emitter, emitter is connected with the negative terminals of the source. So now due to voltage source VCC, so junction J1 will be forward biased. This junction J1 will be forward biased, and junction J2 will be reverse biased. Okay, since junction J2 is in reverse bias, there will not be any current flow inside the IGBT from collector to emitter. So Initially, consider that there is no voltage applied to the gate terminal. So at this stage, IGBT will be in a non-conductive state, that is shown earlier. In the characteristical, you will find it. So later on, we are coming here. So now no voltage applied to the gate terminal, so at this point IGBT will be in a non-conductive state. Now if we increase the applied gate voltage due to the capacitance effect on the silicon dioxide layer, the negative ions will get accumulated on the upper side of the layer and positive ions will get accumulated on the lower side of the silicon dioxide layer. Okay. It is so. So this will cause the insertion of negative charge carriers in the P region. So higher the applied voltage, this VG, greater the insertion of this negatively charged carriers, and this will lead to the formation of a channel between junction 2, which allow flow of current from collector to emitter. That is here. Collector to emitter. So the flow of current is represented. That is, I told you in this picture, these directions. This current is shown when the applied gate voltage increases, the amount of the current flow is also increases from the collector to emitter, also increases. So as I told you in the very first starting, so this is the characteristic which I will discuss later on in details. Now, what are the types of IGBT? So types may be classified into two types of IGBT based on the N plus buffer layer. The IGBT is that having the N plus buffer layer is called the punch 2 IGBT or PT IGBT. The IGBT that does not have any N plus buffer layer are called the non-punch 2 IGBT or NPT IGBT. So based on their NPT IGBT and PT IGBT, that is the non-punch through and punch through, are named as symmetrical and non-symmetrical IGBTs. So the symmetrical IGBTs are the ones that have equal forward and reverse background voltage, and asymmetrical IGBTs are the ones that have a reverse background voltage based on the forward background voltage. So symmetrical IGBTs are mostly used in AC circuit, whereas asymmetrical IGBTs are mostly used in DC circuit because they don't need to support voltage in the reverse directions. So so you get two types of IGBTs. The one is punch 2 IGBT and another is non-punch 2 IGBT. Because of their say N plus buffer layer, these are called punch 2, and N plus buffer layer where it is not there, so it's called non-punch through IGBTs. So now that is the types. Now we'll come with the next. So we get two types of IGBT. One is punch 2 IGBT and another is non-punch 2 IGBT, and they are named as per the say N plus buffer layer presence. Where buffer layers is present, that is called punch 2, and where it is not present, so it is not non-punch 2 IGBT. Now, what is the difference of between these punch 2 IGBT and non-punch 2 IGBT? Punch through IGBT or before doing this difference, we must say this non-punch through IGBT are called symmetrical, and punch through IGBT are called non-symmetrical IGBTs. And this symmetrical IGBTs because they have equal power and reverse background voltage, and asymmetrical IGBTs are have a reverse background voltage less than the power background voltage. So mostly symmetrical IGBT is used in AC circuits, and asymmetricals are used in the DC circuits. They had don't need to be support voltage in the reverse direction. Now, with this, we can draw the differences between punch through and non-punch through IGBTs. Punch through IGBT are less rugged in short circuit failure mode and has less thermal stability, whereas non-punch through are more rugged in short circuit failure mode and has more thermal stability. In punch through, collector is heavily doped P positive layer, and the non-punch through collector is lightly doped P negative layer. So it has in case of punch through IGBT, it has small positive temperature coefficient, constant voltage, hence parallel operation requires great care and attention. This is very important. And non-punch through temperature coefficient of constant voltage is strongly positive, hence the parallel operation is easy. And turn-off loss in turn-off loss is more temperature sensitive, hence it increases significantly at a higher temperature, and turn-off loss is less temperature sensitive in case of non-punch through IGBT, and it will remain unchanged with higher temperature. Now, operation of IGBT as a circuit, since IGBT is a combination of BJT and MOSFET, so let us see its operation and as a circuit diagram. Here is the internal circuit diagram of IGBT, which includes 2 BJT and one MOSFET and another JFET. So gate, collector and emitter pins of the IGBT are marked here. So this is the internal circuit diagram of IGBT. Now, collector of PNP transistors is connected to NPN transistor through this JFET. JFET connects the collector of the PNP transistor and the base of the PNP transistors, and these transistors are arranged in a way, in such a way, to form a parasitic thyristor setup to create a negative feedback loop. So the resistor RB, this one, is placed to short base and emitter terminal of NPN transistors. To ensure why this is sorted, to ensure the thyristor does not latch up, which leads to that means which leads to the latch up of the IGBT. So JFET is used to signify the structure of the current between any two IGBT cells and allows the MOSFET and support most of the voltages. So that's all about the internal say circuit diagram and as this IGBT and its operation. Now, switching characteristics of IGBT will be discussed. This IGBT, is a voltage control device, and it only requires a small voltage to the gate to stay in the conduction state. Once again, I'm telling you, since it is a voltage control device, so definitely it requires a small voltage to the gate to be in the conduction state. And since these are unidirectional device, they can only switch current in the forward directions, which is from collector to emitter. Typical switching circuit is shown here. The gate voltage VG applied to the gate pin to switch a motor. This is motor. This is M. For which apply voltage V positive. The resistor RS is roughly used to limit the current to the motor. See, gate voltage is connected here, switching this motor, and this resistor is limiting this current. So series resistors. This is the typical circuit diagram. Now, input characteristics of IGBT can be understood from the graph given here. Gate voltage and collector current. Graph this like this. No conduction state. This voltage is the release. This is the threshold voltage, and then it will be the collector will flow. So. Say this has 3 stages we are finding here. When gate voltage is 0, so this is in the offset, and called as the cutoff region. When gate emitter voltage is increased, if it is less than the threshold voltage, so then a small leakage current will flow. The device will still in the cutoff region. When this gate emitter voltage is increased beyond this threshold voltage, the device gets into active region, and the current starts flowing to the device. So this flow of current will increase in voltage, this gate emitter voltage. That is shown here. You see the collector emitter voltage is the current. This is the cutoff region. So it is that gate emitter voltage 1. Now it is increasing to gate emitter voltage 2. And it is this region is called active region. So that is the characteristics of this IGBT. Its switching characteristics. Now. How applications of IGBT are used in various applications. I told you the AC and DC motor drives, unregulated power supply, switch mode, power supply, CPS, traction motor, control, electrolytic, inverters. So used to combine and isolated gate effect. The control input and micro switch a single device. So these are some applications. So many more applications are there. So how this IGBT is available in a package form? So package of IGBT is like this different kinds of packages with different names from different companies are available. So for example, NAND technology of through-hole type and surface mount type packages. Through-hole type packages includes TO262, TO251, TO273, 274, TO220, TO220, 3, TO247, TO247 AD, and surface mount package includes TO263 and TO252. So that's all about IGBT. So what we have studied about IGBT is, in a nutshell, what is IGBT, what it is, its symbol, its construction, its working, then how its structure, its internal structure, its working, how it works, then its types, difference between the different types of these IGBTs, then its operation, how it operates as a circuit, then its switching characteristics, and its this is the switching characteristics and characteristics of and applications and available package of IGBTs. So that's all about IGBTs.